Myself, Dr. Rajesh Kumar Yadav, Assistant Professor, PG Department of Physics, SKM University, Dumka. Today, in this lecture, I am going to discuss a simple method of constructing exactly soluble potentials in quantum mechanics. Okay, you have number of exactly soluble potentials, and here we will discuss a simple method how to get the exactly soluble systems and their solutions. This lecture consists of these three parts. First one, in this part we will discuss some of the important quantum mechanical potentials and their connection with the orthogonal polynomials, and the second we will discuss some important properties of the orthogonal polynomials such as Hermite polynomial, Lagrange polynomial and Jacobi polynomial. And thereafter we will discuss this simple method, that is the method of generating exactly soluble system. It's a very simple method. So in general what we do in quantum mechanics, before going to discuss this, in quantum mechanics, to get the solution of a given potential, we solve the Schrodinger equation, generally time independent Schrodinger equation. Suppose for a given potential we have this. For a given potential, this is V of x. Suppose this is one dimension case. We can also consider the higher dimension case also, but let's consider one dimension case first. For this case, if you want to solve this type of potential, what we do, we use the Schrodinger equation by 2m del 2 psi plus V of x psi of x equal to E of psi of x. Okay. This is the usual method what we do generally to get the solution of this given potential. I will discuss this special method or this simple method later on. So first we review this one. What we do generally in this type of potential. So what we do? Where this is the Schrodinger equation. This is the Schrodinger equation, time independent. This is the time independent Schrodinger equation in one dimension case. So, and this del is nothing but this is d2 by dx square, the Laplacian operator, d2 by dx square, and this cross Planck constant which we know already. So for this given potential, if you have the potential given, to get the solution of this Schrodinger equation, solution means what you get, you have to find this psi and E, the wave function associated with this potential, and the energy eigenvalue corresponding to this system. So if you get the solution of this potential, or if you have to find the solution of this type of potential, we generally use the boundary conditions imposed on the wave function psi, and that boundary condition is related to the given potential or the nature of the potential. So solving the potential problem using this method is slightly difficult due to the boundary conditions. So we generally this is not convenient or not easy to get the solution for any unknown potentials. But what we have in this case, if you have the potential, then you can find the solution. But in this simple method, by using this method, you can not only find the solution of the given potential, but you can generate the potential and find the solution of that potential and complete solution, not only so in this simple method we can generate the potential and find the solution, but in this conventional method which we use generally, in this method we can find the solution of the potential only, but we have the given V of x. So this is the normal method which we use generally. Okay. So in quantum mechanics we have some of the important potentials which have different applications in the theoretical physics. For example, you have the harmonic oscillator which have many applications in the quantum physics, like 3D oscillator, Coulomb potential, like hydrogen atom, scarf potential, generalized positron potential, Morse potential in quantum mechanics or in quantum chemistry also, and other branches of theoretical physics also. So we have so many applications of these exactly solvable systems. So it's very important to how to get these exactly solvable systems and how to get the solutions of these type of systems. So let's we briefly discuss, or let's so we have some important potentials in quantum mechanics, and we know that some of the potentials which have the solutions like harmonic oscillator, Coulomb potentials, etc., these potentials are associated with, or the solutions of these potentials are associated with the non-orthogonal polynomials. So polynomials play an important role to get the solution of these types of exactly solvable potentials. Some of the potentials are like harmonic oscillator. This is in this form, half m omega square x square. Second one, 3D oscillator. 3D oscillator, and the potential is generally the effective potential. 3D oscillator. This is the effective potential, or the potential half omega r square simply, but this is the effective potential because in the 3D case we use the three-dimensional Schrodinger equation and we decouple that Schrodinger equation into three one-dimensional Schrodinger equation, and in that case we get the effective potential like this, half m omega square r square plus L plus 1 by r square. Okay, and Coulomb potential. This is also like this, E square by r, and this E square by r plus L into L plus 1 by r square. It's very difficult to write the exact form, and similarly we have this Morse potential, scarf potential, and so on, etc. So these are the important potentials. We mentioned here only 5 potentials. When we discuss this simple method, then we will generate all the possible potentials. What we see, when you find the solutions of all these potentials, the solutions of these potentials are associated with the non-orthogonal polynomials. For example, if you consider this harmonic oscillator and use the Schrodinger equation and solve by the normal method or usual method, we get the solution of this equation is in the form of, this is the solution, in the form of Hermite polynomial h of nx. Okay. Similarly, for 3D case, we get the solution in the form of Lagrange polynomial alpha some function g. So we replace here g, where this g is the function of x. Similarly here, for this Coulomb potential also, this is also associated with this Lagrange polynomial ln(g). This Morse potential is also associated with this Lagrange polynomial. Alpha is a parameter, and this is scar potential. This is associated with Jacobi polynomial. So what we see, most of the potentials in quantum mechanics, the solutions of these type of potentials are associated with the non-orthogonal polynomials. So in other words, we can say these polynomials play important role to get the solutions of these quantum mechanical potential problems. So let's we review some this behavior of these polynomials, or some important solutions, or some form of the differential equations of these polynomials. So let's review. For example, let's review the differential equations associated with all these polynomials, which will be useful in this method also. So for any of these polynomials, we can write the differential equation like this: d2y by dx square plus q of x, the dy by dx plus r of x y. This is equal to 0. So for any of these polynomials, either Hermite, Lagrange, Jacobi, Bessel's, etc., all these polynomials satisfy this type of second order differential equations. And if you solve these differential equations by different methods like power series method, etc., the solution of this differential equation gives this y is in the form of any polynomial, orthogonal polynomial. This may be Hermite, Lagrange, or normal Lagrange, Jacobi, etc. This is the solution for this one, and this q of x, and this r of x, these two this q of x and r of x, these two may be functions of x, may be functions of x are some constant. Okay, this may be either functions of x, either this q may be a function of x, but this r may be function of x, or this may be a constant also. For example, okay, for example, if you consider the Hermite differential equation, which is written as, for example, Hermite differential equation. Yes, for Hermite differential equation, if you consider the Hermite differential equation like this, dy by x square minus 2 of x dy by dx plus n of y equal to 0. In this case, this n is a constant parameter. This may be 0, 1, 2 and so on. Now, if you compare this equation with this equation, we know there is so many. This equation is very important when you get the solution. When we have to find the solution of the Schrodinger equation. So this equation will play an important role, and this type of equation can be mapped into the form of the differential equations of the orthogonal polynomial. So we correlate these equations with the corresponding differential equations of the orthogonal polynomial. So first we consider the Hermite differential equation. In this case, if you compare these two, what we get? We get compare this one with this one, we get this q of x. This may be a function, so q of x is equal to minus 2x, and this may be a function or constant. So here r of x is equal to n. So r equal to n. This r equal to n. Okay. Once we know this type of, and the solution for this Hermite differential equation is y equal to h of nx. Okay. And this y satisfy this y or this polynomial satisfy an orthogonal condition like this. If for any y not related to hn, for any y, the solution is yn. This x, the range depends on the potential or the polynomial. So we put here x, y of nx, mx, some weight function. This is known as weight function. For different polynomial, we have different weight function. So this is known as weight function. And dx, this equal to some constant into delta n. This is Kronecker delta. This is Dirac delta function. Kronecker delta. Okay. So this is equal to this. Okay. In the case of Hermite polynomial, this becomes like this yn, this h of nx, h of mx, and w for this Hermite polynomial, we have this W, the weight function, this weight function e to the power x square. This is nothing but this is Wx, this weight function equal to the power minus x square for this Hermite polynomial into this dx equal to some constant and delta nm, and this constant for the Hermite case is nothing but to the power n factorial root over 5. This is the constant. Okay? This is well known. This is a well known constant. Okay? So for the Hermite case, this is like this, and the range goes to this one. Similarly, in the other polynomial case, Lagrange and Jacobi, you have different u, different r, and for Lagrange and Jacobi case also, we can find the different orthogonal conditions. We have here Lagrange polynomial, and the constant will be different. Obviously, this constant will be different in that case. And once we get the orthogonal conditions, once you know the orthogonal condition which we will use in that simple method when you try to find the set of exactly solvable potentials. So we summarize here these orthogonal conditions. So in the case of if you consider for the Lagrange polynomial, what we have in this case, this q of x and r of x are defined by q of x is equal to alpha plus 1 minus x. Okay, this r of x equal to n, I think this is true, r of x is equal to n, and the orthogonal condition and the orthogonal condition, this is this orthogonal condition will be like this. This is this Hermite is replaced by Lagrange now. It's simple. We can also prove all these conditions, but we have to use some lengthy calculations. X alpha nmx this, and some weight function this, and dx equal to this constant delta n. In this case, this constant and the weight function is defined like this. This weight function will be e to the power minus x into x to the power alpha. Okay, this is the weight function, and this constant quantity will define like this: n plus alpha factorial by n factorial. So this is for the case of Lagrange polynomial. Okay. Similarly, okay. Similarly, for the Jacobi case, okay, this q of x and r of x is lengthy, so this can be defined by this beta minus alpha minus alpha plus beta plus 2 into x divided by 1 minus x square, and q of x is equal to r of x is equal to n plus beta plus 1 by 1 minus x square. Similarly, in this case also, the orthogonality condition can be obtained or written like this. In this case, the weight function w of x, since this q and r, this depends on two parameters, this alpha and beta, so this weight function also depends on two parameters, this alpha beta, and this weight function is defined by 1 minus x to the power alpha and 1 plus x to the power alpha. The weight function in this case 1 minus x to the power alpha, and 1 plus x to the power beta, and the normalization constant or orthogonality constant, this constant. In this Jacobi case, this is lengthy constant, and this constant is defined by 2 to the power alpha plus beta plus 1 divided by 2n plus alpha plus beta plus 1 into gamma of n plus alpha plus 1 and gamma of n plus beta plus 1 divided by n factorial and gamma of n plus alpha plus beta plus 1 delta n. So these are the important properties. Mainly we have discussed only one property, that is the orthogonality condition, which you have to use when we will discuss that method. So these are three polynomials, and there may be also other polynomials. We consider here only three, which we will use to get the solutions of the potentials generated by this method. So these are the Hermite, Lagrange and Jacobi. So today I stop here, and in the next lecture I will continue this topic, and in that lecture we will discuss the simple method, and that method how to generate the exactly solvable system. So thank you.